Hey everyone, so we're doing the back of our study guide right now, and we are talking about heterogeneous mixtures. They are going to appear different. So heterogeneous mixtures, a great few examples would be like trail mix or salads. With that being said, like if I have trail mix, I might get more peanuts or more M&Ms, where you may get more maybe the Chex part. For a salad, I might get more lettuce where you might get more tomatoes. So heterogeneous mixtures can be separated physically again, and they are going to appear different. So wanted to talk about that. When we're talking about saltwater is also a mixture. Now, you're going to see the picture right here. You're going to see that I'm putting salt into the water. And a solute is the substance that's getting dissolved. So I put the salt in right over here and it's going to dissolve. So that's a solute. Then you have the solvent, and that's what's doing the dissolving. So the solvent is what's doing the dissolving. And then you're going to get what? Salt water. Exactly. That's our solution. So as a reminder, when you dissolve salt, which is the solute, into water, which is my solvent, you're going to create salt water. So there's a song. I know you remember it from 6th grade, right? All right. So the solute to the solvent, solute to the solvent, solute to the solvent makes a solution. In this case, it's the salt to the water, salt to the water, salt to the water makes salt water. So yeah, salt is the solute, water is the solvent. That makes your salt water in solution. Make sure you pause for a minute to write this down. All right, let's keep going. Part 4, atomic theories. So the first answer is true. The second answer is true, right? So atomic theories have been modified many times to explain new data, and scientists do need to repeat experiments over and over while they're collecting data. Talking about our famous scientists, right? Dalton and Democritus. They were the first scientists that just thought the atoms were small and hard, and they are tiny, they're indivisible particles that make up matter. We didn't know much back in the day, but as obviously technology and new theories came about, we started learning more. Thomson was the gentleman, the scientist that thought about the plum pudding. Do you remember that? All right. Well, Thomson basically thought that the entire atom was positive, and then there was these, which would be kind of like the cake part, and then there was these negative charges, kind of like raisins, that were the electrons, and that's basically what he thought. His was pretty basic, still a circle. Rutherford kind of had more open space. We're going to talk about Rutherford now. He's considered as the planetarium model. His idea was that there is positive in the middle, right? So absolutely there's a nucleus, there's a positive charge, and these electrons just kind of float around it. As technology continued to get better and new ideas came out, Bohr thought that the electrons now were floating around in these orbits. Okay, so in these orbits, there had to be a certain number of electrons allowed. So in the first orbit, you were allowed 2, second orbit 8, then 18, then 32. And so there's still a nucleus in the middle, but there were so many electrons allowed in each one. And now the modern theory basically is where we have these electrons floating in this electron cloud, and that's what we currently believe today. All right, so now we're going to go to part 5. I'm going to give everyone a second to look at this. All right, what is the difference between image 1 and image 2? Not very much. It's still the same element. All that has changed is that the atomic number, right? So atomic number is my smaller number. That is right here. That's 9 on image 1. And down here, it's just at the bottom. It's the same thing. All they did was they flipped the image. So on the SOL, you're probably going to see a lot of images like this. This is going to be kind of how the periodic table stated. But in a lot of the things you might see online, or when you get to certain chemistry classes, maybe at a later time, you might see it like this. All you need to know is the atomic number is my smaller number. Okay? My mass number is going to be the bigger number, which is usually like with 18.998. It's going to be having, this is a whole number. This is going to be kind of with your decimal. We do round. So we're going to round this to 19, okay? Because it's above 5. So it's going to be going up to 19. So let's talk about, once again, the atomic and mass number are switched. That's the difference between the images. Your element name is fluorine. The symbol is going to be F, and atomic number is 9, okay, smaller number. That is equal to P and E. If you remember ape, A equals P equals E, okay, so they're all 9. Now let's talk about our mass number. I told you guys we're going to round it to 19, and we already know our atomic number is 9. That means how many neutrons we have is 10. Take a minute, make sure you have that. All right, so my mass number is protons plus neutrons. That's located in my nucleus. So here is a Bohr model. We are going to have 9 protons. Those are positive charges. We're going to have 10 neutrons because what we did here was we did mass number minus atomic number to get my neutrons. So 9, 10. And then we have to put our electrons in our orbit. So if you remember Bohr, he said 2, 8, 1832. 2, 8, 1832. So you have 2 in the first or energy ring, right? That means you have 2. Then you can have, how many are left? Well, you take 2 away from 9, that means you have 7. So only 7 are allowed to go in the next one. You could have up to 8, but we don't have all of that. We only have 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9. All right. Whatever electrons are in the outer shell, okay? So you have 1, 2, 3, 4, 5, 6, 7. So you have, did I do that on purpose? I think I did. So there's 7 left in the last orbit or energy ring. That is called valence electrons. So valence electrons are anything in the outer ring. All right. Let's go to part 6, scientific method. 8th grade students are testing how the concentration of vinegar affects the rates of bubbles in baking soda. One student drops the vinegar. The second student watches the reaction, and the third student records the data. The first trial, you have 0 amount of vinegar, which means there's no bubbles. In the second trial, you put 10 milliliters of vinegar. That's 50% bubbles. And then the third trial, you do 25 milliliters of vinegar, which is 100% bubbles. What is your independent variable? What are you changing? The amount of vinegar. Very good. The dependent variable is going to be the amount of bubbles, right? The control your comparison is trial 1 because we have no bubbles. That's the one that's different, right? That one's not getting any. And then if you go back, we have the constants are going to stay the same. Those are the type of chemical we're using, vinegar. That's 8th grade students doing this. Okay. Now we're going to talk about density for a minute. Remember, density, the formula is mass over volume. So I'm going to use a triple beam balance to find the mass of the rock, which is 80 milligrams. I need to find the volume, which I use a graduated cylinder. That's the tool. So the graduated cylinder level is at 10, and then I put the rock in, and the water went up to 18. So we have to figure out what my density is. So I have 80, right? That's my mass right here. And I'm going to do my water displacement. My water displacement is my final number minus my starting number. So 18 minus 10 is 8. That's how I got this. So if I do 80 divided by 8, I'm going to get 10 grams over milliliters. All right, we got a couple more, guys. Doing awesome. The pH scale 0 to 6 is considered acid, 7 is neutral, and 8 to 14 is a base. Okay. Mass, reminder, is the amount of matter, and then volume is the amount of space. And my last question, mass never changes, but weight does. So would I weigh more or less on the moon? I'm going to weigh less on the moon. Okay. Now, this is a fantastic video. This is the last thing I wanted to share with you guys. Reminder, you have a test next class. And also make sure that you do your digital notebook. It is due Thursday at 8 o'clock. So if you're on A-Day right now, please make sure that you get that submitted by 8 p.m. Other than that, please be good, make good choices. After this video, you guys are going to do your stop and goes. So you're going to use an expo marker and write on the laminated sheets, and then you're going to flip over and you're going to see the answers. Please study, and I look forward to seeing you all next class. So you please watch this video, and I will see you soon. Element, mixture, or compound. Do you know the difference? We're all surrounded by matter. To understand this matter, we have to have a way to organize and describe it. Let's look at an example. For the purpose of this demo, a single nut, a bolt, and a washer represents an atom. All matter is made of elements. Substances that are made of one atom cannot be reduced to simpler ones. A compound is a substance composed of two or more different atoms chemically bounded to one another. The nuts, bolts, and washers are all bounded together. This represents how compounds cannot be separated by mechanical or physical means and can only be destroyed by chemical processes. A mixture is a material containing two or elements or compounds that are in close contact and mixed in any proportion. These can be separated by physical means like filtration, evaporation, sublimation, and magnetic separation. We did this last class. All right, you guys think we got it? Let's play a game to test your knowledge. Aluminum, is that an element, mixture, or compound? Element, great job. Water, H2O, is that an element, mixture, or compound? That is a compound. Table salt, sodium chloride, NaCl, is that an element, mixture, or compound? A compound. Is soda an element, mixture, or compound? Mixture. Is salt water an element, mixture, or compound? Mixture. Remember, you can evaporate the water. Is salad dressing an element, mixture, or compound? Mixture. Carbon. Is that an element, mixture, or compound? Element. Baking soda, sodium bicarbonate. Element, mixture, compound. Compound. You can't separate that part back out easily. Iron, Fe, element, mixture, compound. That is an element. Is air an element, mixture, or compound? Air is a mixture. Copper, element, mixture, compound. Element, is this on the periodic table? An eggshell, calcium carbonate, element, mixture, or compound? It's a compound. We've determined that soda, salad dressing, salt waters, and air are all mixtures. To better understand mixtures, you can sort these farther. A homogeneous mixture has the same appearance and composition throughout its mass. In air, the oxygen, nitrogen, and other gases are basically all indistinguishable. A heterogeneous mixture consists of visible different substances or phases that is not uniform. So in salad dressing, you can see that the difference is between oil and vinegar. You can check that out. Is mixed salt water heterogeneous or homogeneous? This picture is going to be homogeneous. What about soda? Hetero or homo? It is homogeneous. All right, but now I'm going to put ice in it. Now it's going to be heterogeneous because the ice is at the top, so it's going to look different. So the importance of understanding all of this is that we have new technologies and it can help us open doors in fields of engineering and other science fields as well. Great job, guys. All right, study hard. I'll see you next class.